Let's quickly review some ideas from robust control that you should have seen in the lecture before we jump into the problem. So we're looking at autonomous systems of the form x dot equal to ax, where this matrix A is uncertain. So later we will generalize this to forced systems. But first let's just look at autonomous systems of the form x dot equal to ax, where a is unknown or uncertain but fixed. So we're looking at fixed uncertainty of this form. Let's say we know something about this uncertainty A, in that A belongs to this set, to this discrete set of matrices. Here I have chosen a set with cardinality 3, so 3 elements. So this A could either be A1 or A2 or A3. Then the question is whether this uncertain system is stable or is robustly stable, and this can be verified by checking the matrices A1, A2 and A3. And if all these three matrices are Hurwitz, meaning that the eigenvalues are in the left half plane, then we can say that this system is robustly stable. So that's basically the idea at the core. This is easy when we have a discrete set here, such as a collection of matrices. Now an alternative problem would be when this set is continuous. So let's look at that. So now alternatively we could have again a system of this form x dot equal to calligraphic ax, where a is uncertain, but now a can be so we know that a is of the form a0 plus delta a1, where a0 and a1 are known matrices and delta can be between -1 and 1. That's just a real number between -1 and 1. So now we have a family of matrices A, an infinitely so in other words we have a continuum or infinitely many A's corresponding to each delta between -1 and 1. Now we can ask the same question, whether this system is robustly stable, or whether is this uncertain system stable. But now we have infinitely many possibilities and we cannot check for all the A's that correspond to each value of delta between -1 and 1. So let's see what we can do with such a uncertain system. So the first solution could be obtained by gridding the parameter delta. We see that delta belongs to this closed interval -1 and 1. We could grid it such as here. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points, 10 grid points between -1 and 1, and on each of these grid points we could calculate the value of A. So we would then have 10 possibilities for the A matrix in this system, and then we can check if all these A's are Hurwitz. So that would be a possibility, and then we could make the grid finer and finer until we're happy to say that for all these A's this system is stable, which means that this uncertain system is robustly stable. So an alternative to this could be using linear fractional transformations and the small gain theorem. And what we do here is that we represent the uncertain system as a feedback loop with a certain and known part and a part that is unknown, or part that is unknown up to some information about it, such as the norm. So let's see how to do that. So our original system was x dot equal to calligraphic ax, where a was of the form a0 plus delta a1. So I just substitute for a0 and delta a1, and as a naive approach I can call delta a1x u and I can call a1x y. If I do that, I can represent this uncertain system as a feedback loop shown here. So we have x dot equal to a0x plus u, but u is delta times y, so there should be a delta times y, and y is a1x. So if we close this loop, we would indeed get a0x plus delta a1x here, which is our uncertain system. And now we know something about this block delta, so let me just replace these deltas by delta we have. So now we have replaced this uncertain system by a feedback loop here. Now we can ask the question whether this feedback loop, let me move this here, or let me just minimize this. Now we can ask the question whether this feedback loop is stable for all deltas between -1 and 1, and I should just say delta, where delta is now delta, small delta times identity, and delta is between -1 and 1. So let's see how this works. So we have this block here. This delta is basically delta 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 delta. So this is a block made up of deltas. So we have y equal to a1x, so we would then get u as delta times a1x, and yes, we have this. So we've replaced a question about uncertain systems of this form by a question about stability of feedback loops as here, and the question about the feedback loop could be then answered by the small gain theorem, and let's see how to do that. So what does the small gain theorem say? The small gain theorem says that if we have a feedback, so roughly it says that if we have a feedback loop with a block represented by a0, I, and a1, which is this block here, and a block delta, then the feedback loop is stable if the product of the norms of this block and this block is less than 1. This is what the small gain theorem roughly says. Now we can use any induced norm here, such as, for example, the H infinity norm. So the small gain theorem allows us to say that if this block here has an H infinity norm of something, and this block here has an H infinity norm of something, then if the product of the H infinity norms of these two blocks is less than 1, then this feedback loop is stable. And if this feedback loop is stable, then we can be sure that the uncertain system is stable. Now we know something more about the delta block. If we know something more about the delta block, such as if the delta block has a norm less than or equal to 1, then this small gain theorem condition, so this would just be 1 at most, and then we could say that by the small gain theorem we can have that if the H infinity norm of the upper block a0, I, a1 is less than 1, then the feedback loop is stable. This for any delta with norm less than or equal to 1, which would mean that we have robust stability, because this is true for our delta, because we consider delta of this form, and we know that delta is between -1 and 1. That's why we know that the norm of delta is less than or equal to 1. So we would indeed have that for any delta between -1 and 1, the capital delta will have a norm less than or equal to 1, and then by the small gain theorem, if this condition is satisfied, then we have robust stability. That is, this uncertain system x dot equal to ax for any A of this form, A0 plus delta A1, where delta is between -1 and 1, is robustly stable. So let's see how we can do better than what we just did in our naive approach. We just, oops, let me just bring this back. So we just said that our system on the top is A0, 1, A1 and 0. So that allowed a delta block of this form, and we proved stability for delta less than or equal to 1, and this was the only condition on delta. But we were interested only on delta blocks of this form, so we're doing not the best as best as we can, but in pulling out the uncertainty. So how can we do better? Let's look at the extreme case when A1, the matrix A1, is of rank 1, or in other words, A1 can be written as some column vector B times some row vector C. If we can do that, we can write our system x dot equal to a naught of x plus delta a1 of x as a naught of x plus delta bc of x, where I've replaced a1 by b times c, and then I can call cx as y, delta cx as u, and I can come up with this feedback loop where now this delta block is just a 1 by 1 system instead of a large matrix as in the earlier case. So let me say this once again. So what we did earlier was to just set a1x as y and delta a1x as u. That meant an identity over here and a1 equal to c. So we split, in other words, we split a1 as identity times delta, we split delta a1 as identity times delta times a1. And because of this, if the state vector was 10 was a 10-dimensional vector, so if x was in R10, our delta block would be 10 by 10, and the Smolian theorem only requires the norm of delta to be less than 1. So this condition here would allow all other delta blocks whose norms are less than 1, for which we are proving stability even if we don't want that. So that's quite conservative. So we can look at an extreme case to get an insight of what we can do, and this extreme case is what we will need for our problem, exercise problem 21.1. So there indeed a1 would be of rank 1. So if a1 now is of rank 1, so now what we do is, now we replace, we write delta a1 as b delta c because of this factorization of a1, and now our delta block is 1 by 1. And now we can use the Smolian theorem again and say that if this block has an h infinity norm less than 1, our uncertain system is stable. So let's try to summarize what we've said. So in summary, we had a system of this form: x dot equal to ax, where a was given to be of this form and delta was given to belong to -1 and 1, closed interval. Now the question was whether this system is robustly stable, that is it stable for any delta between -1 and 1. This question in its original form is not easily answerable because we have infinitely many a's, and we cannot check all possible A's, and that would be infinitely many conditions. So what we did is we wrote this system as a feedback loop. We see that if if A1 can be factored as B times C, where B is a column vector and C is a row vector, then we can write delta A1 as delta BC, and we can write this feedback loop where we set U to be equal to delta times Cx, and we multiply B at the entry of U. So this uncertain system can be represented by this feedback loop, and now we can study the stability of this feedback loop for delta between -1 and 1, and this is where the small gain theorem helps us. Now if we know that delta is between -1 and 1, the H infinity norm of delta is less than or equal to 1 for all times. Not for all times, but for all deltas. And now then the condition via the small gain theorem would be only that this g of s H infinity norm is strictly less than 1, and this we can test by linear matrix inequalities, or more specifically the bounded real lemma, and this is the idea. Now we've converted a seemingly hard or an infinite dimensional problem into a linear matrix inequality, which is clearly a finite dimensional problem. And if we do find a solution in the linear matrix inequality optimization problem, then we can be sure that the H infinity norm of g of s is less than 1, and then we can be sure that this system is stable for any delta between -1 and 1. So that's the idea. And now let's have a look at the forced system case. So this was all for autonomous systems, so here we don't have an external input, but now let's have a look at forced systems and some key questions that we would like to answer in problem 21.1. So now let's look at x dot equal to ax plus bw and z equal to cx, where now again a is uncertain. Let me bring this. Let's just keep it here. So x dot equal to ax plus bw and z is cx, where a is again of this form, but now we have an input w and an output z. So let's first look at the nominal system, which is when delta is 0. When delta is 0, we can define the nominal system to be G0 or GO of S, which is A0, B, C, and 0. And then let's define this set calligraphic G, which is the collection of all systems of the form ABC0, where A is of this form, A0 plus delta A1 of S, which is what we see here, and delta varies between -1 and 1. So this G is basically a collection of all possible systems we can have as the A varies in the given range. And now for such an uncertain system, so this is this one is an uncertain system, and this is this is an uncertain system, and this one is a set of all possible systems within this uncertainty given to us. Now we can ask 4 key questions for such a system. So the first question is nominal stability. So the first question would be, is the system with no uncertainty, or in other words delta equal to 0, stable? So that would be this nominal system. So that's quite straightforward. We can just neglect the uncertainty, just check whether this system is stable or not, and that's true when A0 is Hurwitz. Now the next question is nominal performance. This question again only looks at the nominal system without any uncertainty and checks whether some performance is met, such as for example the H infinity norm less than gamma. Again, this is straightforward, and we can just take this system and plug in the matrices into our LMIs and check whether we can verify this condition. The third question is robust stability, which means or which asks whether all systems in G are stable, and that would be difficult to check, at least in a straightforward manner, because we have this set G, an infinite set, or in other words it's a continuous set, and we have to use the ideas that we just saw for autonomous systems in order to verify whether all systems here are stable. The last question is robust performance, which is asking whether all systems in this calligraphic set G, which is basically a collection of all possible systems, do all these systems satisfy some performance measures, such as the H infinity norm less than gamma. So do all systems G in calligraphic G satisfy this condition? Now for our exercise problem 21.1, we will look at these three questions. We will not consider this one here, but we will look at these three questions and try to answer them. So that's it for the review of robust control. So let's quickly review the output feedback synthesis LMIs, both for H infinity and H2 problems. So we have an open loop, so let me use a different color. So this one is the open loop plant with inputs W and U and outputs Z and Y and states X. We are looking for a controller which is again parameterized by state space matrices AC, PC, CC, DC, which can measure output Y and can exert U on the plant and has states XC. So we can represent the dynamics by pulling out the integrator here, and now this block just represents a matrix with inputs X, W and U. Similarly, the controller can be represented by a matrix with the integrator in feedback loop here. Now this is just a matrix with inputs XC and Y and outputs XC dot and U. Similarly, this is a matrix with inputs X, W and U and outputs X dot, Z and Y. And that's also one reason why I show signals flowing in this direction, because then we can look at this matrix multiplied by the vector X, W and U. So we're looking for matrices AC, BC, CC and DC that make the closed loop system stable. So closed loop system from W to Z stable, and minimize some norm of the closed loop system, either H2 or H infinity. So let's represent with K the dynamics or the variables AC, BC, CC and DC. Then we can close the loop here from Y to U by substituting AC, BC, CC and DC and obtain calligraphic A, B, C and D as closed loop matrices. And now again we can pull the integrator out and represent this like we did here. So now we have zeta as the states, which includes X and XC, the states of the plant and the states of the controller. The input, the external input is W and the output is Z. So now we can compute the calligraphic A, B, C, D closed loop matrices. We can do this as follows. So let's first look at this plant. here. So from W to Z we had the plant A1, B1, C1, D1, and that's what. So the inputs to the closed loop now are X, XC, and W. So X is in the first channel and W is in the third channel. So we would just have to permute A1, B1, C1, D1 as here. So because we have in the first channel X and in the last channel W, we still get A1, B1, C1, D1 here. Now the controller gets inputs XC and Y. XC is the second channel, so we have XC as the second channel and W as the third channel and X as the first channel. So we have this first row picks out XC and brings it here, and the second row is C times X plus F times W, and that you can see here is just Y. So the controller is getting XC and Y as input, and the outputs are XC dot and U. So the U is, then if you observe here, we have B and E multiplying the U. So BU is going into X dot and EU is going into Z. So we have B times U going into the first channel, which is computing X dot, and E times U going into the last channel, which is computing the Z. And in the second channel we get back the XC dot, and that's why we don't need anything else here. We already have XC dot after this. So you should really think about these matrices well, and make sure that you understand this before you proceed. Now once you have this one, then it's simple matrix multiplication to obtain the final closed loop matrices AK, BK, CK, and DK. So this one is AK, BK, CK, and DK. Note that the controller parameters AC, BC, CC, and DC are shown in green, which are embedded here, and that's why we write the calligraphic A as a function of K, which is the controller parameters, which we represent by AC, BC, CC, and DC. So that's the closed loop. Now if someone gives us the controller, then we can directly check whether the closed loop is stable and if the closed loop satisfies some norm, some H2 or H infinity norm requirements, and that's given to us by the analysis LMIs. So the analysis matrix inequalities are given here. So this is for H infinity control. So if someone would have given us the controller, we could just plug the K here and look for a P positive definite that satisfies this inequality, and if AC, BC, CC, and DC are known, this would be a linear matrix inequality. But now because we have unknowns AC, BC, CC, and DC, and if we try to look for a P and AC, BC, CC, DC that satisfy this, this is no longer a linear matrix inequality but a non-linear matrix inequality with variables P, AC, BC, CC, and DC. So note that we have non-linearities because of these products A times P. So for example, we have A of K given by this thing here, and if we take the product of A with P, we would definitely have products with blocks of P and DC, AC, BC, and CC. So we have products here and here. So the nonlinear terms are this one and this one, which make testing this condition hard. We could then think of a congruence transformation with a matrix calligraphic Y and obtain equivalent matrix inequalities. So P positive definite can be equivalently written as y transpose py positive definite. So let me just write that as well. Positive definite, and we can similarly make a congruence transformation with y0 0I to this one and obtain this condition here. So this matrix here, and then the condition would be this matrix negative definite. Note that a congruence transformation here would just mean we multiply the first row, first column from the right by y, and that's why you see y is here, and we multiply the first row by y transpose, which is just multiplying y from the left, and that is what you see here. So that would be equivalent matrix inequalities. And now the idea would be to have or to choose a y such that the matrix inequalities on the right are linear. So we can similarly do this for H2 synthesis problems, where the analysis, so if someone gave us the controller, we would have to check if there exists a p positive definite such that let me change the color, such that this LMI and this LMI holds. But now, because we have unknowns AC, BC, CC and DC, we have products here, and so this is a non-linear matrix inequality, which would verify that this system ABCD closed loop from W to Z has an H2 norm less than the trace of Z, which is another variable here. I should add this to LMI variables. And now we have products between P, AC, BC and CC here. So we can again do the same thing. We can think of a congruence transformation with a matrix Y and transform these three inequalities to Y transpose PY positive definite. Again, as we did before, we use the matrix Y0 0 identity for the congruence transformation of the second matrix inequality, and if we do that, we would then multiply the first row from the right, from the left by Y transpose, and the first column from the right by Y, and this is what you see here. We have Y transpose in the first row and Y in the first column from the right. Similarly, for the third inequality, we would have Y transpose PY again, which we already saw here, and then Y multiplying the first column from the right, and Y transpose multiplying and the first row from the left. So now if we observe the conditions for H infinity, so these were the conditions for H infinity synthesis. We had the terms like Y transpose P AY, Y transpose PB and CY appearing here in the transformed matrix inequalities that would have to be linearized by a clever choice of Y. Now if we compare this with the H2 conditions, we essentially have the same terms. We have Y transpose, so there's a bracket here. We have Y transpose PAY, Y transpose PB and CY, which is appearing also in the H2 synthesis inequality. So if we made a clever choice of Y for the H infinity case, or let's say if we made a clever choice of Y such that these three terms are linear in some new variables, then we would also have, with the same choice of y, the same three terms linear here, so we would solve both problems with the same choice of y. And now let's see what choice of y does the job. So if we split the matrix P into blocks X, U, U transposed, and something we don't care about, and we again split the matrix P inverse into Y, V, V transpose, and something that we don't care about, we would have first of all P, because P times P inverse is identity, we would have XY plus UV transpose equals to identity. This we will use later, but now with this splitting of the matrices P and P inverse, we can select the Y to be YV transpose, so the first column of P inverse, and identity 0 as the second column. So this choice of Y essentially does the job of linearizing these three terms. And let's also quickly see how. So if we collect all the terms of interest that we have to linearize in a matrix like this, so we have Y transpose P A of K Y, B transpose P Y, C Y, and D. So note that we don't really need to do anything here, but we just keep it here so that it makes writing things down a bit easier. So if we consider the matrix given here and plug in the Y, the clever choice of Y that we just proposed, so Y V transpose, let me also use the same notation, color notation here, use that one for Y and that one for V. If we select this Y, plug it in here, if we plug in this split up of P in here, and if we plug in the closed loop A of K, P of K, C of K, D of K that we computed here, so we take the A of K, P of K, C of K, and D of K here, and we plug all these three things in this matrix, so Y, P, and A, B, C, D, we get something like this. Now at this point I encourage you to really pause the video and verify for yourself that this is in fact true, that you do in fact get, after you substitute Y, P, A, B, C, D here, this equation, this expression here. And now what we've done is we've collected the linear terms outside this bracket, so here everything is linear, there are no products, but inside these curly brackets we have the products of X and Y, and the products of AC, BC, CC, DC with X and Y. And so if we now define this whole thing inside the bracket to be KLMN, we do have a linear inequality, or so this matrix is equal to this one here, because we just substitute this curly bracket here with KLMN, and then we can just take the products to see that now this matrix has no products, where we've introduced new variables, obviously KL, M, and N, and let's call all these variables V. So now we have, with this choice of Y, this term equal to this term, which is linear in Y, M, K, X, N, and L, and the second term is this one, B transpose PY, with that choice of Y will give us a linear term in X, N, and L. Similarly for C and D, so this term and this term. And let's, because now these are linear terms, let's call these terms A of V, b of v, c of v, and d of v, where this function is linear in v, where we've just defined v to be all the new variables x, y, k, l, m, n. An interesting point to note is that if we look at this substitution k, l, m, n equal to this thing here, we see that n is in fact equal to dc, and you should also verify this for yourself once. Okay, what happens to y transpose py? We can see that by just substituting our choice of y, we get y transpose py equal to yiix, and let's call this x of v because this is again linear in v, and v is the collection of all these variables, and there are no products here. So now what we've essentially done is that if we go back to the matrix inequalities, we've made a clever choice of y so that these terms are all linear in the new variables v for h2 and also for h infinity synthesis, because essentially the same terms appear in both the problems. So if we now try to write down the final h infinity output feedback synthesis problem, we look for these LMI variables x, y, k, l, m, n, and gamma that satisfy these inequalities. So what we've done is basically just replaced y transpose py by x of v, replaced y transpose pay by a of v, and it's transposed y transpose pb by b of v, and so on, where a of v, b of v, c of v, and d of v are linear in v. So this is now really a linear matrix inequality which can be solved by convex optimization techniques. Similarly, we can now write down the synthesis LMIs for H2, where we've again just simply replaced y transpose py by x of v, y transpose pay by a of v, and so on. So now we have indeed again, even for H2 output feedback synthesis, linear matrix inequalities in the new variables v. Now please note that for the H2 synthesis problem, we actually additionally had one more condition. So let me just add it here. Because that condition poses no problem, I did not put it inside the slide, but that condition was that the closed loop D has to be equal to 0, because if that is not so, the closed loop matrix system is not strictly proper, and that would have an infinite H2 node. But this is really no problem, because as we saw earlier, so if we look at d of k is t1 plus edcf, and so that is nothing but t1 plus edcf equal to 0, and because dc is left untransformed and it has no products with any other variables, so what I mean is there is no d appearing anywhere else in the LMIs, we could just put that condition as it is here. So we would have to add another condition, which is t closed loop of d of k, which is t1 plus e dc f, which is nothing but t1 plus e n f, and that's because we just saw that n is untransformed, or rather dc is untransformed, and dc is just equal to n, so we can just add this additional constraint. So dc equal to n can be observed here, so that additional condition could be also incorporated here. So now that's the general procedure for obtaining synthesis LMIs, and we can solve these LMIs using CVX, for example, and obtain the variables v. But we still need to go back to the control variables a, c, b, c, 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 and dc. So we have to reconstruct our controller from the new variables x, y, k, l, m, n, and that we can do by simply looking at this one here. So we had equated this term in the bracket to be equal to k, l, m, n. Now we can just solve for a, c, b, c, 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 d, c by first subtracting x, a, y from k, l, m, n, and then inverting from the left and from the right using this factors. What we still need to do is to compute the u and the v, which are required for computing these matrices, which are not amongst the usual LMI variables. And in order to do that, we use this condition that we had obtained from the fact that PP inverse is identity, and then we can just simply do an SVD, a singular value decomposition of I minus xy, and obtain u and v matrices like this. You can also note again here that in fact dc is just n, so this transformation basically just assigns dc to be equal to n. So that was just a side remark. So that's the general procedure for obtaining synthesis LMIs from analysis LMIs. So that's it for this part of the review. So let's now finally look at the problem 21.1. We have a spring mass system here with unit masses, so the masses are equal to 1. The spring stiffness varies between 2 and 0.5. We can exert a force via the controller on the mass 1, and we have disturbances d1 and d2 as forces acting on the two masses. We have to neglect the friction here and assume perfect rolling. And yes, so that is the physical setup, and the uncertainty is inside this k. So the k is unknown but fixed. We have this fixed and unknown uncertainty. The control tasks are to bring the output, which is only the position of the second mass, to 0 in the presence of disturbances d1 and d2. Some more specific control goals are to look at the impulse response from at d1 and at d2, and to make sure that the settling time is so that y of t is less than 0.1 is less than or equal to 15 units. We have to also make sure that the control input has to stay within plus minus 1. So these are the control goals, and let's try to do this problem now. As we saw in the review section, we have to look at a robust problem now because the system is uncertain and we have to find a controller that robustly stabilizes the system and at the same time maximizing the performance for the nominal system. So we are looking at the problem of robust stability with nominal performance. So here you see again the open loop plant dynamics have substituted the mass equal to 1. So you have an A matrix which is uncertain because of the K, whereas B matrices here, the input matrices, are fixed along with C. So let's first look at the case when we grid the K, like we discussed in the review. So if we now grid the K from 0.5 to 2 with an interval of 0.3, we get 6 grid points, namely 1, 2, 3, 4, 5, 6 grid points, and for each grid point we will get an A matrix. And now in order to compute the input and the output matrices in the uncertainty channel, PQ channel, we can follow the procedure outlined in the lecture. You can have a look at that in the lecture, and there is code where you can see how this is done, but I will now not focus on that one but try to do this by direct calculation. So we have K varying between 0.5 and 2. We can first compute the mean or the average of 2 and 0.5, so that's the center. Let's call this the nominal stiffness, K0, and now we can write the K as K0 plus some delta which varies between minus 0.75 and plus 0.75. So that covers the whole range. Now we can write the matrix A as some constant matrix or the nominal matrix A0 plus delta tilde. So this is delta tilde, which varies between minus 0.75 and plus 0.75, times this matrix here, which is minus 1, 1, 1, minus 1. So that you can see we'll just add this delta tilde at these places. Now we can clearly see that this matrix is rank 1 because we can write this matrix as a product of a column here and a row matrix and a row vector. So you can see that this column multiplied by 1 is just the first column here, multiplied by the second entry minus 1 is the second column here, and then we have all zeros. So now we can say that this A is A0 plus this matrix, let's call this B tilde, let's call this matrix these are all column and row vectors seen as matrices, C tilde. So we can write A0 as B tilde, delta tilde, C tilde, but the delta tilde varies between minus 0.75 and plus 0.75. So we can define a new variable delta which is 0.75. So we can define a new variable delta which is defined as delta tilde over point. So delta is defined as delta tilde divided by 0.75, so that we get delta tilde equal to square root of 0.75 times square root of 0.75 times delta. And now we can pull these things inside the B tilde and the C tilde to get the B and the C, which are nothing but square root of 0.75 times C tilde, and B is also square root of 0.75 times B tilde. And now we have a delta which varies between minus 1 and 1. So we've then represented A as a constant nominal part plus a column vector B times a row vector C multiplied by delta, which varies between minus 1 and 1. Now once we have this set up, we can define a feedback loop that corresponds to the uncertain system. So here we see the uncertain system here, where A is uncertain. We can write the A, as we just saw, as A0 plus some column vector B times some row vector C times delta, where delta varies between -1 and 1. Now this uncertain system can be written as a feedback loop, where we can now, let me take this out, we can define input P as delta times Cx, and so if we split this, so let me just show how this is done. We have Ax equal to A0x plus P delta Cx, and now if we call P delta Cx as P and Cx as Q, we can have a feedback loop going through this delta channel. So Q is Cx, that is going through delta and coming back as P and then multiplying BC. So this term, if we substitute for P Cx, delta Cx, we get P delta Cx here, and that can be added to this term to get A0 plus P delta C times X, which is an uncertain system. So we've represented our uncertain system as a feedback loop, where the uncertainty is now pulled out in this delta, which is just a real number between -1 and 1. So once we've done that, we can now come to the design of a controller K here. Now I've just pulled the uncertainty up. Everything is the same as here, but now I have a controller channel which is measuring Y and exerting U on the plant. So we have x dot as A0x plus BU plus B1D plus B tilde P. So let's actually call this PP so that we know what we're talking about, and that is in accordance with the notation CQ. So for our problem, BP is in fact the column vector B, and CQ is in fact the row vector C that we just saw above. So now we have this loop, and now we have pulled out the uncertainty delta here, and we know that this delta varies between -1 and 1. And now this problem is to design a controller K so that we have some guaranteed nominal performance from the disturbance to Z, and we have robust stability, meaning that for any value of delta between -1 and 1, our system, our closed loop system, is stable. So in order to do that, let's look at now this block diagram, which sort of represents a transfer function blocks. So this block, which is the same as this block here, has inputs P, W and U, and has outputs Q, Z and Y. Q is going via the delta block, entering as P. W is the disturbance channel, and we have U as the control input and Y as the measurement. Now if someone gives us a controller, we can just plug it in and close the loop from Y to U to write the closed loop system as H. Let's call the closed loop system H, which depends on K. But now let's assume that K is given. We can then close the loop and have this as the closed loop system with inputs P and W and outputs Q and Z, where the Q is being fed back via the delta block into the P. So now let's ask the standard questions that we posed in the review section. So now let's look at what do we mean by nominal stability and nominal performance. So for this one we neglect the uncertainty channel delta, and we look only at this block shown in red here, so which is the block from W to Z and the feedback from Y to U via K. So let me just mark it again. So this block, that would be the system for studying nominal stability and nominal performance. So this is shown again here, and for a given controller the closed loop is represented by HZW. Because it depends on K, we write it as a function of K, and that has input W and output Z. Now the question about nominal stability and nominal performance is basically just this: is HZW stable, and is HZW satisfying some performance measures, such as performance criteria, such as the H infinity norm less than gamma. So that's nominal stability and nominal performance. So now let's look at robust stability. So now let's consider robust stability. So here we do consider the complete closed loop system that we had above, so this one, without neglecting any blocks. So now if we represent the same system in this form here, we can verify that this is the same as this. Let's see, Q is HQP times P plus HQW times W. So Q, which is here, is HQP times P plus HQW times W, and P is then delta times Q, whereas Z is HZP times P plus HZW times W, which is here. Now you can see that this loop has a parallel, this feedback block diagram has a parallel structure. So the only feedback loop is shown here in blue, and we can check the stability of this loop via the small gain theorem. So how do we analyze robust stability for any delta between we always keep in mind that delta is known to be between -1 and 1. So the answer is as follows: if this loop is stable for all delta between -1 and 1, this loop, and if all the other transfer functions are stable, then we do have robust stability. So the condition for loop being stable is then given by the small gain theorem. The small gain theorem basically then just says that this loop is stable. So says that loop is stable if the norm of HQP of K is less than 1, because we know that the norm of delta is less than or equal to 1. So this we already reviewed in the previous section, so that's the idea now. Now let's see how do we obtain LMIs for these conditions that we saw above. So we see here again the system, except that now I've removed the delta block. So there was a delta block here, and the Q was going via this delta block and entering as P in the channel. Now this system without the delta block is shown here when we close the loop from y to u. So that's the closed loop system now without the delta block again. So q is supposed to go from here and enter SP. Now we just saw that we have robust stability of the system if the HQP norm is less than 1. That would imply from the small gain theorem that this small loop, this loop here, would be stable. Additionally, if all the other transfer functions are stable, which are these, then we would have robust stability. So these are the conditions for robust stability. And now we would like to maximize the performance for the nominal system, and the nominal system we saw above is just HZW. So this would be the nominal performance measure. So let's see how to obtain LMIs for this optimization problem. So we now write the system again as we saw in the review, but now we have it in this form. If we have an integrator, we can write this as a matrix. So that's our open loop system with PW, which is our disturbance here, and U as input channels, Q, which is the uncertainty channel, Z as the performance channel, and W the control measurement. So from these matrices, these are known to us. Note that we have A0 here because we have pulled out the uncertainty in the QP channel. So from these matrices we can easily define the HZW system and the HQP system. Sorry, this should be GZW because this is still open loop, GQP system. So these are still the open loop GZW and GQP system. So with inputs U and W, which is our D, and outputs Z and Y. Here we have inputs P and output Q. This is the uncertainty system, so GQP from P to Q, and again outputs Y, which is measured by the controller, and control input U. So now we want to design a controller K that at the same time achieves a closed loop H infinity norm of this system. So HQP of K is the closed loop system when we close the loop via this channel here. So that's HQP of K. So we want to find the controller K, which is basically just the matrices AC, BC, CC and DC, such that the closed loop HQP of K is having an H infinity norm of less than 1. So that would be the condition for the small loop to be stable, this loop, because of the small gain theorem. And we want to have nominal performance, so the HZW system, which is again depending on K, that is when we close this loop here, that system is having an H infinity norm less than gamma, and the overall closed loop system H is stable. So the closed loop eigenvalues are in the left half plane, and this makes sure that this condition is satisfied, which is nothing but these three transfer functions being stable, along with this one of course, but for this one we have an additional condition. So now let's look at the linear matrix inequalities that we can write for these two systems. So we can write for the GZW system and the GQP system, these two linear functions of A. Now at this point you should be familiar with the linear matrix inequalities for H infinity synthesis, which we just reviewed in the previous section, and you should be familiar with the linear in V functions, so A of V, B of V, C of V, and D of V, which are the linearized versions of the nonlinear matrix inequalities. So please review the H infinity output feedback synthesis if this is not clear. So for the HZW system, we can write A of V, B of V, C of V, and D of V. We call this A norm, B norm, C norm, and D norm for the nominal system. And we can define for the robust system A rob of V, P rob of V, C rob of V, and D rob of V. Note that the A matrix or the A of V is the same in both. What changes is only the B, C, and the D, and that is because if we go back to this one, we see that the things that are changing are simply the two, so the second column and the second row, which is the input output channel. So in the GW case, we have from W to Z, that's why we have C1 and D1 here, and for GQP we have the input P and output Q, so we have CQP, DQP, DQU here, and BP and DYP in the second column. So only those things change when we compare these two. And now we can generate LMIs for these two systems by simply writing down these conditions here. So we get again these matrices, these LMI matrices, and note that for the robust control system we only need a gamma of 1 because we only need the H infinity norm of GQP to be less than 1, whereas we want to minimize the gamma nominal. Note that we also required H to be stable, but that is already achieved because we have A transpose P plus PA in the 1-1 blocks of these conditions, which means that if K is Hurwitz, which means that H is stable. Now let's look at the final LMIs. So the final linear matrix inequalities look something like this. If there exists xy KLMN, which we call V, such that this is true, so this we called xv positive definite, such that A, so this is for the nominal performance, and note that we had a 1 here, and that's for robust stability. So now we can solve these LMIs for xy,k,l,m,n. Once we have these variables, we can reconstruct the controller by the standard techniques that we saw earlier. Note that we can now even minimize gamma norm subject to these LMIs to obtain as good nominal performance as we can. So to construct the controller, we from the obtained xy, k, l, m, n, we follow standard procedures. We already saw this in the review. So we basically just do an SVD of I minus xy, obtain the u and the v, and get back the matrices AC, BC, CC, DC from this transformation. And you should again go back to the review section if this is not familiar. So that's it for this problem. Let's look at the code and the results finally. So here you see some sections of the code. So first we have a function which designs a controller for the nominal system. We define the WS and the WK, and this should be familiar by now. We define the generalized plant, and we find an H infinity optimal controller here. We could here for the nominal system also use this Hinf sin command to get the controller and the closed loop. So for the LMIs, we define X of V, A of V, B of V, C of V, and D of V, as we saw in the notes. So we define these matrices. So this is still for the nominal system, and then we minimize comma subject to these constraints. So LMI1 is just X of V positive definite, and LMI2, this is now the output feedback version of the boundary real lemma. So this is what we just derived, A of V plus A of V transposed, P of V, and so on. So this is the nominal control synthesis for H infinity output feedback. We can get back the controller by doing an SVD of I minus XY, and then computing the control matrices as we saw in the construction of the controller part. Now let's look at the nominal response. So this is the impulse response for the disturbance inputs D1 and D2. We see that for all inputs the control action is between -1 and 1, so we don't have any input saturation, and we also see that the settling time is less than 15 seconds, because at 15 seconds we already are at 0.08, and we don't go above that one in the future, and the same is the case with the impulse at the second disturbance channel. Now let's look at how robust is the nominal controller. So now we perturb the spring coefficient randomly. So here we see a few trajectories with a random perturbation of 0.1 around the nominal K0 of 1.25. We see that with such a small perturbation, the nominal controller is still able to stabilize all the trajectories, although the performance for some might be a bit worse than others. So these are now results with a perturbation of 0.2, still with the nominal controller that we designed. Now here you see that clearly for some values of spring stiffness K, the performance is really poor with the nominal controller. Now with a perturbation of 0.3, you see that the nominal controller is no more able to stabilize some trajectories. So there are some values of K within plus minus 0.3 that the nominal controller is not able to stabilize. So clearly the nominal controller is not robustly stabilizing for delta in the range minus 0.3 to 0.3. So now we go to the robust design, or in other words, we now try to maximize the nominal performance subject to the constraint that we have a robustly stabilizing controller. So what we can initially do is see the trade-off between nominal performance and robust stability. So this plot now shows with the increasing values of delta K how the nominal performance changes. So the lower the value of gamma, the better the nominal performance. So you see that for small values of delta k, we have quite low value of gamma, and as we increase this delta k, what we are asking the controller to do is to stabilize all possible systems. So remember that these are in fact really infinitely many systems where we have the value of the spring stiffness between 1.25 plus minus delta k. So for example, if we compare these 2 points, if we have a delta k of 0.4, we are asking the design or the optimization problem to find a controller that is able to stabilize all systems with a spring stiffness of 1.25 plus minus 0.4, and at the same time minimize the gamma for the nominal system k0 of 1.25, and the output is this gamma. So what we get here is the fact that for any system, so the controller that we get out of this design is able to have this as the nominal performance for k0, but is able to stabilize all systems with k equal to 1.25 plus minus 0.4. Note that this is not robust performance. This is not saying that for all systems with k 1.25 plus minus 0.4 we have this performance, but only for the nominal system. What it is only saying is that it's stabilizing all systems. Now if we compare this point here, we are asking the design to find a controller that is stabilizing all systems with k equal to 1.25 plus minus 0.8, and at the same time minimizing gamma for the nominal system. And clearly, because now this controller has to stabilize many more systems, it can only achieve this performance for the nominal system. So the nominal performance is sort of sacrificed at the cost of robustness. So that's the idea here, and that's sort of the point of this whole exercise. You can see the two controllers, two extreme controllers. So this one is with delta almost equal to 0, so basically just the nominal design, and this controller is the one for which is robust for delta k plus minus 0.75. Oh, sorry, this is plus minus 0.5. Now these are the results with the robust controller. Remember that the nominal controller failed to stabilize systems with a perturbation of 0.3 or more. Now we do see that with a perturbation of 0.5 we do have a stabilizing controller, and that's mainly now because of the additional LMI that we add to the previous nominal LMI. So this is obviously at the cost of reduced performance. And finally, with a perturbation of 0.75 we do again have a controller that is able to robustly stabilize a perturbation of 0.75, which was what the problem asked, but now at the cost of an extremely poor nominal performance. Nominal performance. And now you can go back to the code and really tune the shaping filters and try to get as much nominal performance as you can while maintaining robust stability. And that's all I wanted to discuss for this problem. Thanks a lot.